I can see a lot of people attempting things. I can also see people texting the board to other people. Tell that person to come to class. Get in here, man. All right, so we've got this stuff. Let's sketch the k equals 2 level curve. Okay, so for k equals 2, we do the same intersect calculation. All right, so we get plus or minus root 2 for our x-intercepts. Okay, then for our y-intercepts, the 2 and the 2 cancel out. And we get plus or minus 1. Okay, so we're kind of drawing that over top of this diagram. We get something like this. So we get another ellipse. Root 2. And you get another concentric ellipse. If we imagine things, how this would go for general k, right? Just for any number k, we'll get some ellipse, right? And they'll all be concentric ellipses. So this gives us a picture in our mind of what the graph should look like. Every time I cut this thing, I get some ellipse. Okay? So yes, you've got the right idea. So make this shape with your hands. Okay? Imagine something where all the level sets are ellipses. Okay? Yes, good. Cradle the ellipse. Right. And that's kind of the shape we were envisioning, right? It's thin in one direction. It's thin in one direction, fat in the other direction. Every cut of this thing is going to be an ellipse. Right, so that inner shape there is a representation of our k equals 2 level set. If you've got a laptop out, I highly encourage you to just play around with this thing. Go to GeoGebra and just be like, whoa, ellipses. Right? There's 2 level sets. Three level sets. So I highly encourage you to muck around. We're going to keep coming back to this as a theme. Contour plots, they let us take high-dimensional things and reduce dimension by 1. So if we have something whose graph is usually 4-dimensional, if we take level sets, we get a 3-dimensional graph. So this is going to be helpful. Right, we took something 3-dimensional, our graph became 2-dimensional. So this gives us insight into what's going on in front. Yeah, we'll leave that there. Okay, now we're going to shift gears. We're going to move to some new stuff. We're going to head over to limits and continuity. Okay, so we're going to get into section 4.2 of the book. So just to take a step back to our last calculus class, in one variable, things are so special. Things are so nice in one variable. Okay? In one variable, what needs to happen for a limit to exist? Yes?
The limit from the left and the right.
Yeah, the limit from the left and right need to agree. Right? If those are the same value, then the limit exists. Okay? This is super duper duper nice. This is like a beautiful condition. So you can imagine our number line, we've got some special value, x is equal to c. If we approach from the right, sorry, if we approach from the left, we should get the same value as we approach from the right. The real numbers are one-dimensional. There's only two directions of approach. How does this differ from the two-dimensional situation? What happens in 2D? Yes? Yes. So just to amplify that a bit, the comment was there's infinitely many directions of approach. So in two variables, there are infinitely many ways to approach a point. Okay, so in one variable, you can approach from the right or you can approach from the left. In two variables, if we have a point x, y, then we can come towards that point from many, many different directions. We can come at it from here, or here. We can come at it from here. What makes it even more subtle is that there's like weird, like wiggly paths that approach, right? There's not only infinitely many directions, there's infinitely many paths. Right? There's lots and lots of ways to go to a place.
So if you were able, let's say you had all these paths, for the limit, you just have to come to that point. So if you can find at least two different paths that don't approach that point, does that mean the limit doesn't exist?
Yes, that's brilliant. Yes, what that guy said is great. So just to let me rephrase, there's infinitely many paths to check for the limit to exist. If two paths do not agree, the limit does not exist. Did I get that correct? Yeah. Okay. Can we all just say that together? There are infinitely many paths. Yes, good. I feel like that's some kind of like spiritual teacher or something. There are infinitely many paths. Okay. If two do not agree, the limit does not exist. Good, yes. Good, yes. Okay, so let's write that down. Okay, there are infinitely many paths. Two do not agree. Okay, the limit does not exist. Okay, very, very, very big and important point. So most of the time, we're going to be showing that limits don't exist, okay? Because the check to show they don't exist is a lot easier. So let's, oh, there's a question? Right, right, so we'll talk about that. We'll talk about how to do that with polar coordinates and stuff. But yeah, most of the time we want to show things do not exist. So let's come up with an example of how that could go. Actually, wait, I should write down the formal definition for this thing. Okay, so we say that the limit of a two-variable function is equal to c if when we limit along a particular path. So what this is a parametric equation for our path. Okay, so we say the limit is the constant c if the limit goes to c along all parametric paths through that point. Okay, so that's sort of the formal mathematical definition. So I want to do an example of computing a limit along a path. Okay? So here's a particular path. Right, so if we specify a path, then we can convert this two-variable limit into a one-variable limit. So we'll just plug in the path to this thing. Using this, we input x is equal to t, y is equal to t. So this limits to the 0 along that path.
Why wouldn't it be allowed to just plug in 0, 0?
Right, so yes, so here is an example where we can plug in 0, 0. right? Because when we put in 0, 0, this thing's defined. Right? This is actually defined at 0, 0. In our next example, we're going to have a function that's not defined at 0, 0, so we need to approach it from all the paths. So we'll see an example that's not defined at 0, 0 in a moment. Okay. So that's what it means to calculate a limit along a particular path. We take our parametric equation, put it in for x and y, and then limit along that parametric equation. Okay. So here's a function where plugging in 0, 0 would give us 0 divided by 0, right? That's problematic. 0, 0 is not in the domain, but we want to try and calculate the limit there anyway. I want to graph this thing. Graphing these in 3D is very hard, but it'll give you a sense of what the function's doing. So we'll just graph it to see what the function looks like.